Hola, hi, this is Al Nozal, your statistics instructor. Let's get to work. In this short video, we will talk about the classic simple regression model. Okay? So, the simple linear regression model relating y to x can be expressed as follows. Y equals beta 0 plus beta 1 times x plus epsilon, or if you want to underline the dependence of y on x, y given a particular value of x equals beta 0 plus beta 1 times x plus epsilon. Okay? This model says that the values of y can be represented by a mean level. This guy here, that would be, if you want to be specific, that would be the expected value of y given the value of your predictor x, right? Beta 0 plus beta 1 times x would be the mean level, okay, of y for a given value of x. And on the other hand, what we have here, this epsilon, right? What we have there are random fluctuations, and those random fluctuations cause the values of y to deviate from the mean level. Okay? Makes sense? A few comments are in order. The mean value, beta 0 plus beta 1 times x, is the mean for the response variable corresponding to a particular value of the predictor x. Okay? Another comment: the unknown parameters beta 0 and beta 1 are the y-intercept and the slope of the line that represents the means, the mean level. Okay? A third comment: epsilon is an error term that describes the effects on y of all factors other than the value of the predictor x. Now, that's the simple regression model. Let's move on. Let's talk about the classical simple regression model. Let me copy and paste this. It's going to be faster. So what's special about these classical simple regression model? Well, it has the following assumptions. Okay? 1. The first assumption has to do with the individual values of the error term epsilon. Okay? What we're going to be doing here is we're going to be assuming that the epsilons are statistically independent of one another. Okay? And these values represent a random sample from the population of possible values at each level of x. Okay, so let me just say that individual value of the error terms epsilon are statistically independent of one another. Okay? Two, the second assumption in the classical simple regression model. For a given value of x, there can exist many values of y, and therefore many values of epsilon, the error term. So, moreover, the distribution of possible epsilon values for any x value is normal. So that's the second assumption, right? That the epsilons have a normal distribution. Okay? Let me write it down here. Epsilons epsilons, oops, yeah, let me just say it like this. Epsilons are normally distributed. Okay. For any x value. Great. Okay. Assumption number 3. The distribution of possible epsilon values have equal variances for all values of x, right? So this case we could just say that epsilons have equal variances for all values of x, the predictor. Okay. In some textbooks you will find the following notation. You will read something like IID, meaning that the epsilons are independent and identically distributed. Okay, so let me introduce that notation here. Notation. Epsilons are independent and identically distributed. IID and we are going to have a normal distribution with mean 0 and a common variance sigma square. Okay, that sigma square is the same regardless of the value of the predictor variable x. Okay. Number 4, assumption number 4. The means of the dependent variable y for all specified values of the independent variable x, right, can be connected by a straight line called the population regression model. Okay, so if we want to be if we want to write it in a kind of a shorthand notation, what we could do is something like this. If we want to again stress the dependence of the variable y on the value of the predictor, we would say that it's the expected value of y given that we have a particular value for x, right? And what we said is that it's going to be well represented by a straight line. So bottom line, what I want you to see is that the classical simple regression model has these assumptions about the error term, okay? That the errors are normally distributed, they have a common variance, and they are independent. Okay. Now that we have a theoretical understanding of what the classical regression model is, let's try to understand it from a more practical perspective. We're going to do a simulation to do that. Okay, so now what I would like you to do is go to Quarkus and find the slides that go with this video lecture, right? The lecture notes corresponding to the classical simple regression model, okay? Because we're going to need them, okay? Let me find them for you. I have it here. I have those lecture notes here, that PowerPoint. And let's go to slide 25. Yeah, 25. So the idea is the take-home message. What I want you to bear in mind after doing this example that we're going to be doing together is that regression provides estimates of true parameter values, okay? Not the true values. Make sense? Okay. So in this particular example that I prepared for you, we're going to be talking about a company that produces some generic items. Some people refer to those as widgets. And the production takes place in batches, right? So in this case, Y represents the production cost for a given job, a batch, and X represents the number of items, widgets, produced during that particular job. Okay? So what we want to do here is using regression to study the relationship between X and Y and identifying the additional cost per widget produced and the fixed cost for any job. Okay, so that's the ultimate goal, trying to find a mathematical relationship or trying to summarize that relationship using a mathematical model. Okay, so let's go to the next slide. Okay, slide number 26. Here what I have is an interesting data set that I came across. Okay, so we're going to be, as I said, trying to understand the classical linear regression model from a more practical perspective. And to do that, we're going to be using simulation. And in order to carry out those simulations, we need R. Okay, and as usual, our first step when using R will be having or reading a data set, analyzing a data set. So first we have to acquire that data set. Let's launch R. Okay. Now what I would like you to do here is go to File and open a new document or new script. And then I want you to copy and paste these first 3 lines, these commands from R onto that new script. Okay. Why am I asking you to do this instead of copying and pasting onto the R console? Well, it turns out that this URL where the data set is located, it's kind of long, and if we break the line, then R is not going to be able to find that data set. Okay, let me make it a bit bigger here. That's better. Okay, so again, what I just did was I copied and pasted that onto a new R script. Now things should go as planned. Okay, because what I did is now this guy should be here. Oops, let me do it again just to be super sure that everything is going to go well. So copy, paste, and I'm just, you know, making sure that it's a single line. Okay, nice, it went well. Anyway, we know that if we want to see what's inside an object that we have created, or in this case a data set that we have read, okay, all we have to do is just retype the name of that object, in this case prod C. Okay, so it seems like we have 40 observations and 2 different variables, cost and the number of widgets. Okay, okay, so we have the data. Nice. Next step, we would like to be able to use the names of those variables. Okay, so just copy and paste this as is. In this case, we don't have to change anything. For this one, as I said again, it's just that we wanted a single line to avoid problems that wouldn't be able to find our data set anyway. So in this case, it should be fine. It would just copy and paste directly onto the R console. And as you can see, when you want to comment something in R, you use this hashtag, and then everything that follows in that line is going to be ignored by R. And this semicolon is letting R know, we're trying to be very specific, you know, that's the end of that line. Anyway, this hashtag is going to allow you to comment your R programs. So the new command that we have here is names. That's a built-in command, and that is going to show us the two names of the variables, right? But those are the names. What we want to do is we want to be able to use them. So in order to be able to use those names to refer to those guys when we are you know, doing our program, we're going to be using another command called attach. So attach, then when we type, for instance, cost, oh, it's, you know, the column corresponding to that variable. Okay, we get to use those names. Great. So something that it's always a good idea when you're doing a linear regression analysis is plotting your data. Make a graph. Okay, so in this case we're going to make a scatter plot, and to do that we're going to be using that command plot, and the syntax of that function is first you're going to place the name of the variable that goes on the horizontal axis, and then the variable that goes on the vertical axis. So in this case we are interested in predicting cost. So this one goes second, that's the y, and this one goes first, that's the x. Okay. So as you can see from that scatter plot we just made, the relationship between variables, widget, and cost, that relationship seems to be roughly linear, and the variations with respect to that imaginary line appears to be constant, meaning sigma square, the variance, or sigma, the standard deviation, seems to be constant for all values of the predictor, meaning in this case the number of widgets produced in that particular batch. Okay, so before we continue with our simulation, another take-home message is when you analyze regression data, you assumed that your data have been produced at random by your regression model, right? So the random generation model is reasonable if the original data are similar to the simulation data. So in this case, this is the original data. Okay? Now let's do our simulations. So when you're doing a simulation, you're basically playing God, because you know the parameters that produced the data. Okay? So in practice, it is not like that, because if you knew the parameters, you wouldn't need to use these statistical techniques, right? So again, with these statistical methods, what you're trying to do is estimating the unknown true parameters that produced the data. Make sense? Okay, so here we go. So in this case, let me put it again here. In this case, what we're going to be using for our simulation are particular values of the parameters. For the y-intercept, we're going to be using 55. For the slope, we're going to be using 1.5, and we're going to be using a value of 250 for sigma. And those values will be used in our simulation, but again, in practice, they are unknown. Got it? Okay. So now, if I remember correctly, here we have to go to slide 30. There we will find the our commands we need to carry out our simulation. So again, what we're doing here is proposing values, right? That could make sense. So I created an object called beta 0, and I'm assigning the numerical value 55 for that guy. Okay. Something similar for beta 1. This one, remember, represents our slope. Sigma, standard deviation of the error term, of the epsilon term. Now this command, this special R command, length, is going to give you the number of elements in that variable, in the variable cost. Okay, so n 40. Yeah, we knew that we had 40 observations in the original data set. Okay, so here we go. This is where we're carrying out our first simulation, and I'm naming that first simulation sim cost 1. Okay, we're simulating the cost for the first time here, and I'm using a beta 0. I am assuming that that's a good value for the y-intercept. That beta 1, 1.5, times you know, the number of widgets produced in that particular batch, plus, and then we are adding an error term, an epsilon, right, with a mean of 0 and sigma. Can you see that what we're doing here is basically using the classical simple linear regression model, right? With these, assuming that these values, 55 and 1.5, are the values for the parameter y-intercept and slope, and with this 250 representing the other parameter, the other unknown quantity, sigma, that represents the standard deviation for the error term, for those random fluctuations. And then the next line is something similar, right? But they are going to be different because these guys are random. And by the way, that R norm function is going to be, in this case, that R norm is going to be generating n numbers coming from a normal distribution with mean 0 and standard deviation sigma at random. Okay, so let's copy these guys. So let me show you what we have here. So we have 40 numbers, 40 simulated numbers, and in this case Those are the simulated costs, right? Okay, you could do the same with the second simulation, right? And well, they are going to be different numbers. Now, this parameter, this command par stands for parameter, right? So what we're going to be doing here is we want to make a matrix of plots. This mfrow command is telling R that we want to create a matrix of graphs with one row. That's what this first number represents, and that 2 represents the column, the number of columns that we want in that matrix of graphs. So we're going to be plotting these two guys, these two scatter plots, at the same time for both our simulations. Okay. So these two scatter plots from our simulated data, well, they look similar to the scatter plot from the actual data. So it seems that our model is reasonable. The next step will be coming up with a more formal way of proposing the values for our parameters beta 0, beta 1, and sigma. Be patient, we will be doing that soon in the near future. Okay, so let's recap. In this video, we talked about the assumptions made in the classical simple regression model. Basically, we're assuming that the relationship between the mean level of y and x is linear, is represented by a straight line. We are also assuming that the random fluctuations with respect to this mean level, if you want to call it that those random fluctuations, the epsilons, are independent and have the same distribution, a normal with mean 0 and variance sigma square, regardless of the value of x, right? Well, that's it for now. Please take care and keep working hard. See you next time. Bye.